Welcome. In this video series, we're going to be introduced to derivatives and some shortcuts to derivatives rather than just using the definition of the derivative of a function. But to begin, we are just going to reiterate that definition in our warm-up. So we have two different types of functions here, and we want to use the definition of the derivative of a function to find the derivative of each of these. And then just as a reminder, if we're looking for the derivative of a function f, we would notate it as f prime of x, and that would be found by doing the limit as h approaches 0. And then in the numerator, we'd have f of x plus h minus f of x, and then divide the whole thing by h. Okay, so I encourage you to pause the video, try these derivatives on your own, resume the video when you're ready to see and hear the solution. All right, and I've written out the solution, so here we go. So for the function that is just a constant c, a constant number 1, 2, 22, whatever, we just get that f prime of x would be equal to, okay, limit, and then f of x plus h is c, right, because it's c for any x, and then f of x is c, so c minus c in the numerator all over h, that just gives us a whopping 0. So the derivative of a constant function is 0. And then if we look at g is a power function. Power functions are just like x to a power. And so if we look at that, that is a little bit more complicated, but still possible for us to do. So still, f of x plus h, so x plus h all to the power of n minus x to the n, which would just be f of x all over h. And then we do have to expand this via the binomial formula. So we'd have x to the n, and then a bunch of other things, which we can capture as in this summand, and choose I times x to the power of n minus I h to the I, from I is equal to 1 to n. And then, so all of this, just to be clear, this right here, that is your f of x plus h. And then we have minus f of x, which is x to the n. The x to the n's would cancel. We divide it all by h. That should be an h, not an n. And then we get this nice little compact expression. But then when we expand that out and write it out, we'd have n to the x to the n minus 1, n times n minus 1, times x to the n minus 2 times h, and then the rest of the terms thereafter would contain an h, and then when we send the limit as h goes to 0, all of those things would just drop out, and we'd be left with x to the n, or n times x to the n minus 1. And so those are our first two derivative rules. We get the constant function, which we saw. Derivative of a constant is 0. And derivative of a power function, which is just x to the n, would just be n x to the n minus 1. And I actually want to clarify. So the book talks about this as the n has to be a positive integer. I'm actually going to say, okay, so 0, it doesn't, well, 0 is kind of boring. But we can actually say that n is within the set of rationals, okay? Q, so like 1/2 works as well, okay? It's just that typically we don't, when we talk about power functions, they are things that have positive integer exponents, okay? But it actually, this process extends to be for anything with that looks like x to a power, okay? And so if we want to do some quick examples here, we'll do them together. So here, to find f prime, I would take, this is a variation of a power function, but the 5 would come down in front, so I'd have 5 times 3, x to the 4, 5 minus 1, and some of you can just do, could probably just skip to 15x to the 4th, and that would be fine. This next one, not a power function exactly, but again, we could rewrite this a little bit, so it'd be 2x to the minus 2, right? Move that x into the numerator, make the exponent negative. And then we're like, oh, okay, I would bring that down and then decrease the power. So g prime of x would be -4, -2 times 2, x to the power of -3. We have to decrease the power by 1, which is actually going more negative. Okay? And then for h, apply a similar trick. So it'd be 3 and then square root of t to the -3, but we can actually write it a little bit differently yet from that. T to the minus 3 all to the power of 1/2. And finally, we can say that's really t to the negative 3 over 2 by laws of exponents, right? So then that gives me h prime of t as negative 9 over 2, okay, 3 times the negative 3 halves, t to the negative 5 halves, okay? So we didn't have any constants, but notice that in here we actually just, if we had a constant involved, since it was times the power function, we just left it there. That's actually coming up in a rule that you'll see in the next video. Stay tuned.